Welcome to qnawire.
For part A, we're going to find the physical length of the pulse as it travels through space and time. So to find the physical length of the pulse, we're just going to call L for length. Consider the fact that the length is going to be equal to the speed of light, c, times the distance between each pulse, delta t, or the between each pulse, delta t. Delta t is just our t value, so just ct. 14 picoseconds, or 14 times 10 to the minus 12 seconds. Plugging these values in, this is equal to 4.20 times 10 to the minus 3 meters, or 4.0 millimeters. You could write either way, but I'm going to write it as millimeters. Part B wants to find the number of photons per one pulse. The number of photons per one pulse, we can call this in gamma just standing for photons. This is equal to the energy of one pulse, which we call E, divided by the energy of one photon, the energy of one photon being hc lambda. Planck's constant, speed of light, and lambda is the wavelength in units of meters, so we'd have to convert nanometers to meters. Plugging these values in, we find that the number of photons is 1.05 times 10 to the 19. For part C, we're going to use the diameter of the cross-section, which is 0.6 centimeters or 6.0 meters, which we call D, to find the number of photons per cubic millimeter. That's because the number of photons per cubic millimeter, which we're just going to call little n, is equal to the number of photons from part A divided, from part B in gamma, divided by L times 1/2 pi r squared, or pi d squared over 4. So gamma, because it's pi r squared, so that'd be r is 1/2 d, so that's pi d squared over 4. So now, because this is the number of photons per unit volume, okay, so now all we have to do is plug in d in L, and in L being found in part A and B, and we find it equal to 8.2 times 10 to the 16. And this is photons per millimeter to the minus, per millimeter cubes is just per millimeter to the minus 3. We can combine it in as the solution for part C.